Okay, welcome back. So we're going to study parametrizing rotations in 3D. So let's take some easy cases. How do we describe a rotation about the x-axis? Well, that's pretty easy because the x-axis nothing much happens, so that's where we have this 1. And then in the yz we have a 2 by 2 matrix as we would have encountered before. So this is an easy thing to do. Let's consider rotation about the z-axis. And this is also easy because so recall that these are the x, y and z components. So in the x and y plane we have a standard 2D rotation matrix. On the z-axis nothing much happens, so that's why we have these simple rotation matrices. But what do we do in general? That's the question that we'll study in this lecture. What about the general case? So there are many different ways of specifying rotations in 3 dimensions, and let's consider what they are. First is orthogonal matrices. This is very natural. This corresponds to the fact that rotation is a linear isometry. But orthogonal matrices are redundant because you have a 3 by 3 matrix, so this corresponds to 9 parameters. But there are really only 3 genuine parameters. So these 9 entries in the matrix are redundant. And we'd like to get at the true degrees of freedom of the problem, which corresponds to axis of rotation and the amount of rotation. There are some classic techniques out there. Euler angles is one of them. Quaternions is another one. This is a generalization of the idea of complex numbers, which can be used to represent rotations in 2 dimensions, to a technique that works for representing rotations in 3 dimensions. And this was quite a big deal when it was invented in the 19th century by Hamilton, who was one of the great mathematicians and physicists of that period. However, the method that I like does things in a much more direct way. And what it does is that it tries to give us a way to go back and forth very simply between orthogonal matrices and what we should think of as the fundamental natural representation, which is we specify rotation by giving the axis of rotation and the amount of rotation. Once you have that, we should be able to write down the orthogonal matrix. Conversely, given an orthogonal matrix, we should be able to write down what's the axis of rotation and amount of rotation. So we could do this in the easy case, which we saw on the previous slide. Right? For rotation about the x-axis and rotation about the z-axis, you could do this. But my question for you is, suppose I have an arbitrary axis. I just give you some unit vector in R3, and I give you some amount of rotation. Can you construct the rotation matrix for me? Conversely, I could give you a rotation matrix and I could tell you, okay, tell me what's the axis of rotation, tell me what's the amount of rotation. Before we proceed with the lecture, you may want to stop it right here and try to think about how you might do it. And you may then realize that it's a slightly tricky problem. So in this lecture, we'll figure out an efficient way to do this. The big idea is that we are going to represent rotations as exponentials of skew symmetric matrices. Okay, so there are some mouthfuls in here, including the term exponential of a matrix, what's a skew symmetric matrix, but hopefully by the end of this lecture you'll find that all this is very natural. The skew symmetric matrix is going to turn out to correspond to the axis of rotation. So what we're going to do is we're going to take this axis of rotation, and from that we will construct a skew symmetric matrix. We will then construct the exponential of a matrix in some way, and that exponential is going to give me the orthogonal matrix. That's the basic story. And then how do we go back? Essentially, for an exponential, the opposite, the inverse function is the log, and something like that will work out here. So let's start by some review. So you all know the notion of a vector product or cross product from physics. So if I'm given two vectors v1 and v2, I've shown them here as vectors v1 and v2, we can construct the so-called vector product or cross product, which is yet another vector w. And there are properties of this vector w. It's going to be in, we construct the plane of v1 and v2, and then the vector w is going to be perpendicular to that plane. And its magnitude is related to the magnitudes of v1 and v2 and the angle between them. So the vector w is perpendicular to the plane spanned by v1 and v2. So you can review this if you have forgotten this definition. I want to just say as well that I will use an alternative notation. Instead of just using the cross, I will use this wedge symbol. But I use this for cross product. So nothing big deal, just a particular notation that I like and is used in more higher mathematical applications. Okay, the next thing we need to know about are skew-symmetric matrices. Skew-symmetric matrix is defined by the property that a matrix A is said to be skew-symmetric if A is equal to minus A transposed. So this is just the definition. But this definition tells us something. So if I have a 3 by 3 matrix A, then it must have zeros on the diagonal, and if it has entries A, B, C in the off diagonal position here, then the entries here must be minus A, minus B, and minus C. So it's a 3 by 3 matrix, but it has only 3 parameters. And what we are going to do is we are going to take the axis of rotation, which is a vector in three-dimensional space, and we are going to map it to a skew-symmetric matrix. And there is some black magic involved here, and which will become clear later. And let me just remind you that in this course and in this lecture, you may come across concepts that you are a bit rusty on. You may have encountered them somewhere in your previous linear algebra or physics class or calculus or wherever, and now you may have forgotten them. Well, if you need to revise them, just go look them up on Wikipedia, and I find their entries on mathematical topics to be excellent. Okay, so now let's build up from this connection of vector product and skew-symmetric matrices. So this is just the definition of vector product, which is the standard definition of vector product. I'm given a vector A and a vector B, and then the vector product is another vector, and this is what the components will be. So this you can look up. Here is a new idea. We are going to take a vector A. So this is a vector in R3, and we are going to make a matrix A hat, which is a 3 by 3 matrix. And the way we are going to do this is that we are going to take the entries of A and put them at particular locations in this matrix. So the vector A has the entries A1, A2, A3. I take these entries A1, A2, A3 and I put them in particular locations of this matrix. And now I've got a new matrix A hat. So A hat is a 3 by 3 matrix. Okay, this is just some little bit of juggling around. I've just, nothing big deal so far. The fun begins here. Given this matrix, this 3 by 3 matrix, and now I do a vector matrix multiplication. I multiply A hat and the vector B, which is given by the 3 components B1, B2, B3. And you have to just do this algebra. Take this matrix and take this vector and do the matrix vector multiplication. And you will get this guy, which is the same as this guy. So in other words, this matrix vector product does the same job as creating the vector product or the cross product that you're familiar with in physics. So we have established a certain very natural, simple relationship between skew-symmetric matrices and this process of creating a vector product or cross product. Okay, what's the value of this? This is just a little mathematical trick. The value will come soon. For that, I have to build up another notion, which is that of exponentials of matrices. Exponentials of scalars, you know. I mean, here's a classic formula. E to the x is given by 1 plus x squared upon 2 factorial plus so on. That's the Taylor series expansion. Okay, what is the exponential of a matrix? So here A is some matrix. What's the exponential of a matrix? It's kind of a moral equivalent of this formula. But instead of 1, what is 1 in the space of matrices? Well, multiplying by 1 leaves the number unchanged. Multiplying by what matrix leaves a matrix unchanged? It's the identity matrix. Instead of x, well, the objects here are matrices, so this should be A. And this should be A squared upon 2 factorial. What do I mean by A squared? Well, it's matrix multiplication. Matrix A multiplied by matrix A. Plus the matrix and so on. So this is a formal, it's like a Taylor series, but we can use this to define the exponential of a matrix. And in certain programming languages, such as in MATLAB, you in fact have a function called EXPM. So if you do EXPM of A, that says matrix exponential of A, that will in fact compute e to the A. So this is really a perfectly reasonable object, just like the e to the x that you've known and loved since the days of high school, really. Okay, now why is this idea of matrix exponential useful? Let's do one more little trick. Let me remind you that exponentials arise as solutions of linear differential equations. So suppose we have the equation x dot equals ax, where x dot really stands for dx upon dt is x dot. That's just the standard notation. The solution to this differential equation is that x as a function of time is given by x of 0. This is just the initial condition, times the exponential e to the at. Again, standard result. This idea applies when we have x's which are vectors. So here I have this formula x dot, but this is now a vector, and it's this is the differential equation. So what's the solution of this differential equation? So the solution here is going to be x of t equals e to the at, and then there will be some initial condition x of 0. So this is just the initial condition, and this is of course a vector, and e to the at is of course another vector, but that's my matrix exponential. So that's a matrix exponential. So this is all very nice because the notion of scalar linear differential equations gives rise to an exponential. You have vector differential equations, and now you get a matrix exponential. Okay, so now proceeding right along. I want to remind you of this equation, which you probably encountered in freshman physics. So this omega here is the angular velocity vector. So we have the position of a point q, and then q dot is the time derivative. So q dot is given by omega cross product with q. we can rewrite this using this new trick that we learned, which is that when we want to construct a vector product, we will make up a new matrix omega hat, and now we will convert it into a matrix vector multiplication. And the solution to this differential equation, so now we've got a linear differential equation, and the solution to this differential equation is, as we studied in the last slide, it's going to be given by the initial condition q of 0 times the matrix exponential e to the omega hat t. And we can work out what e to the omega hat t is. It's going to be given by this Taylor series. Now, we actually don't have to compute it in this way, which is to really compute each of these terms and then add them up. There are much more efficient ways of doing this. And the reason why there are much more efficient ways of doing this is because these terms, omega hat t squared, omega hat t cubed, omega hat t to the fourth power, and so on, these are not all independent. After a while, if you work these out by brute force calculation, you'll find that they start to repeat, so you can group these terms together and so on and so forth. And I'll give you a little flavor of that by showing how we can calculate the second term in this series, the square term. So the square term will correspond to the product of two skew-symmetric matrices, and I've shown those here. If you work this out, so suppose we have the matrix S hat, and then we have S hat squared, which is the product of these two matrices. Well, that will turn out to be S transpose minus I, and this is a straight algebra thing to do. But let's go back to the formula. It turns out that if we collect these even, odd, and even terms and do a little bit of work along the lines that I just illustrated, you can derive a very beautiful formula, and that beautiful formula is called Rodriguez formula, and it is given by this expression. This is really a beautiful formula. Why? Because given an axis of rotation, and what's the axis of rotation? The axis of rotation here is given by S, and the axis of rotation here corresponds to this omega vector normalized. So I have taken the omega vector and divided by its magnitude. So I have a unit length vector S. Given this unit length vector S, I can make up a matrix, a 3 by 3 skew symmetric matrix, and put that here. Okay. What is phi? Phi is the total amount of rotation, and that is given by the angular velocity omega multiplied by time. So the angular velocity might be in radians per second, time is in seconds, so phi will be measured in radians. So if you look at Rodriguez formula here, we have S hat and S hat squared, which are these skew symmetric matrices that you can construct if you know the axis of rotation S. And then we have phi, which is the amount of rotation, which you know. So given these, we have the ability to construct R, which is the total rotation matrix. So if you want to think about this conceptually, the S hat, the axis of rotation, in a way it specifies infinitesimal rotation, what happens in a very, very small amount of time. Now this process, when you carry it for a finite amount of time, that's what gives rise to the finite rotation, which is R. So it's really a relationship between rotation when a finite amount of time has elapsed to the amount of change when a very, very small amount of time has elapsed in some intuitive sense. But this relationship here is a mathematically rigorous relationship. I'm trying to just hand wave my way to give you an intuition about this. Okay, now we have achieved our grand goal, which is how do we go from rotation matrices to an axis angle representation or vice versa. So how do I go from, given an axis of rotation S and an amount of rotation theta, to R? Well, from S we can construct this S hat. So S is a vector and this is the skew symmetric matrix. And then we can do just this exponential, and that gives me R. Now this can be simplified further, and that is Rodriguez formula. Okay, so that's how we can go from an axis and amount of rotation to the matrix R. How do we do the converse problem? I give you a 3x3 rotation matrix and I want you to tell me what's the axis of rotation, what's the amount of rotation. Well, you actually can do the equivalent, the inverse of exponential, which is log, and it turns out that in MATLAB there is in fact a command by which you can take the log of the R matrix and that will give you theta S hat. But there are other ways. Let me show you how we can get the angle theta, the total amount of rotation. Well, it turns out that the trace of R, and what's the trace of R? It's the sum of the diagonal entries. This is equal to 1 plus 2 cosine theta, and you can verify this from Rodriguez formula. So since we have the rotation matrix R, we can compute theta, so we know the amount of rotation. What about the axis of rotation? What can we do? Well, here's one observation. Compute the eigenvector of R corresponding to eigenvalue one. Because what's the property of the axis of rotation? When you apply the rotation, the points which lie on the axis do not change. So that's why they must correspond to an eigenvector of eigenvalue 1. So that's one way of doing it. But there are a zillion other ways. You can take Rodriguez formula and manipulate it around. So you can use Rodriguez, and you can have R and the matrix R transposed, and then from these you can kind of pull out S hat. And once we have the S hat matrix, you can easily read out the axis of rotation. So we have thus achieved our grand goal, which is to be able to go back and forth between rotation matrices, which are orthogonal matrices, 3x3 matrices, to an axis of rotation and amount of rotation representation. Now we can choose whichever one makes most sense for our purposes.